So good evening. So today's week 10 of the live sessions for the course of Introduction to Fluid Mechanics. I'm Dev Malora and I will be taking this session. So we will be today solving questions related to assignment 9 where topics related to the Reynolds transport theorem and Reynolds transport theorem and conservation of mass and is discussed. So we'll go through these problems and develop our concepts as we do that. So the first question here is related to conservation of mass. So it's saying equation of conservation of mass can be derived from Reynolds transport theorem. And if it is given that there is no generation or consumption of mass in the system, then which of the following statements is true? So two statements are given, and we have to say which of these statements are true, or if both are true or both are false. So, what are we discussing here? We are discussing the equation of conservation of mass, and where it is defined from? It is defined from Reynolds transport theorem. So, can you recall what does the Reynolds transport theorem says? What is Reynolds transport theorem? Why we use Reynolds transport
To establish the relation between control volume and control mass system.
theorem? Yes, sure. So we can like definitely do that, but uh, yes, through Reynolds transport theorem, um, like for example, you may say that control mass systems have uh, like when we are talking about studying dynamics of certain bodies, then we have relations already established for control mass systems, and we want to study for control volume systems, and the relation between those two is given by my Reynolds transport theorem. That is definitely correct. But apart from that, like we can also use Reynolds transport theorem for any property which is likely to be conserved, or we can have a conservation relation if we include some generation or consumption terms in it. So let's say property B within a control volume, and we are trying to write a conservation relation uh, for this particular property. So Reynolds transport theorem helps us achieve that, right? So what are the different terms in this Reynolds transport theorem that we have? All the since it is we are taking a control volume, which is an extended system. The terms that we will have in Reynolds transport theorem are integral terms. Hmm. And in certain cases, as you know, like popular examples, like while deriving your Navier-Stokes equations or the continuity equation, what we do is generally shrink this control volume arbitrarily. So if we shrink this volume arbitrarily, then we have a differential equation since the volume can be arbitrarily small. But in general, a Reynolds transport theorem will give us an integral equation in the integral sense. So generally, there are three terms. So like we can like use this first example, first option for as our example itself. So what is the first term? So here conservation of mass is there. So this generic property is my density. It can be something else as well. It can be momentum, rho into v. It can be my vorticity, or it can be temperature. We get the energy equation. So different equations can be derived using my Reynolds transport theorem or using the framework provided by Reynolds transport theorem. We can achieve like different equations. Uh, so what does this first term say? The first term is giving us the how much it is changing inside the how much the property is changing with respect to time inside the control volume, right? So it's a transient term. This is the transient term. So the amount of decrease or increase of the property inside the control volume is given by this first term. What is the second term?
Flow rate.
Yes. So if there is some increase or decrease happening inside my control volume, then then it must be happening due to some reason. So one of the reason may be that some of that property might be escaping or coming inside my control volume. So there can be a flux in and out of my control volume. So for example, here means for the density here we are using density. So this is basically conservation of mass. So inside my integral it is density. So basically we are uh, checking the mass flux. So in the second term is the mass flux which is coming in and out of the system. So this is basically like dmdt if we write in terms of my mass. So this only like if we expand this we will get this integral formula. This might be some special case which we will discuss later on. But the idea is this is dmdt, the mass changing mass inside the control volume, and this is like my mass flux. So this dmdt plus my whatever mass is going out, rate of this. So mass flux out minus mass flux in. So mass flux out minus mass flux in is how much is total mass which is going out. So total mass which is going out and my mass which is changing. So dmdt is mass which is increasing. So like subtraction will be equal. So if I change the signs, then I think since both of these are in the same side of zero, so the signs will be opposite, right? If mass is increasing, then we can subtract the mass going out and mass coming in, then we should get zero. When we will get zero? If there is no generation term, as it is like the assumption is already there, no generation term. So generation or consumption is my third third term, which is zero here. So that is the generation, right? So in case of my momentum equation, what will happen in this generation term? Generation term, we will have the force. Inside this generation term, we will have force. For momentum equation, for temperature, for like thermal, it will be in like uh, heat heat sources and all will come under this generation term. For energy equation. Okay, so now let's look at this particular equation. So this equation is given and it is said this is applicable when the control volume moves with the velocity of fluid, and control volume can be deformable in this case. Is this true?
False.
Is this false? Why is this false?
So because in the first step we have taken the differential inside because we are
Yes.
considering the control volume as non-deformable.
Hmm. Right.
And in the second term, the velocity is the relative velocity.
It should be relative velocity when control volume moves, but we have not taken that, right? That's
Yes.
correct. Uh, So here we had already discussed. So this term is dmdt. So this term is dt of m, and if we expand m, this will basically be my rho dv, right? Throughout the volume, and this whole thing will be under differential if I expand dmdt. And if my volume is constant, it does not change with my time. Like control volume is not deformable, it is a fixed control volume. Then I can take this inside because control volume is fine. Take the differential inside. we have already taken this differential insight, means we have used the assumption that control volume is not deformable. So this second statement is false. Control volume can be deformable. This is false. And also, if I look at my second term, so the first statement was control volume moves with the velocity of fluid. And so velocity of fluid itself is u. U is the velocity of fluid, and if it moves with the velocity of fluid, then this u velocity cannot be used as my flux. Hmm. It should be the relative velocity, because relative to the control volume, I am checking whether the flux is coming inside or coming out. Hmm. So instead of u, if it were some relative velocity, we should uh, like modify this and take the relative velocity. So some u minus some relative velocity b can be used. Okay. So let's see the. So this is false. This statement is false. Let's see the like next statement. So the next statements, the equation is also given. So you can see this equation corresponds to when the control volume can be deformed. So here the differential is outside. So this equation uh, would be valid for deformable control volume. And also in the second term also you can see the relative velocity has been taken, right? So what is the statement? Statement is it is applicable only when control volume and fluid both move with a velocity v. So is this true?
No, sir.
This is not true. Why?
Because both control volume and fluid are moving with velocity b, so it is 0.
So control volume is moving with in this case control volume is moving with my velocity v, right? But what is the
Yes, sir.
velocity of fluid?
B, sir.
Fluid velocity should be u, right? U is my fluid velocity. So let's say I have a control volume, and this control volume is moving with my velocity v. Now in this term what I want to calculate? I want to calculate how much mass is going out. So for how much mass is going out, I need to see this uh, edge. Let's concentrate on this edge. How much fluid is moving out? Hmm. So if the fluid velocity is also v, what is the flux? Flux is zero, right?
Yes, sir.
Because this edge is moving with the fluid. Now, if my fluid velocity is not exactly v, it is some arbitrary u, which is the generic case, right? If control volume moves, fluid need not move in the same velocity. It may move in some other arbitrary velocity. So let's say u is that velocity. So to calculate my flux, which velocity I should use? I should use my velocity u, by which the fluid is moving, minus my velocity v, through which my control volume is, right? This is the
Yes, sir.
relative velocity. So u minus v is the velocity to be used. Okay, and that has been used here. So is this applicable only when control volume and fluid move, both will move with a velocity v? That is not generally the case. So u can be different from v. Still, this equation will be valid, right? This equation is valid even when u and v are unequal. That is the point. So this only statement is actually wrong. This is a very generic representation of conservation of mass using my Reynolds transport theorem. Okay, is this clear? Uh,
Sir,
yeah.
sir, if in option B the only term was not there,
Mm,
if it was
option
given, No, sir. I'm asking if
Yes.
if
Okay.
if in
If
option B only
this
was not there,
only was not there. Okay. Let's like if I say only is not there. Okay. Then
then is the statement correct or wrong?
so the equation this is applicable when control volume and fluid both move with a velocity v. Definitely this is correct. If my fluid move with a velocity v, then b minus b will be zero. So if I have to then substitute u is equal to b, right? If I can
Yes,
substitute
sir.
u is equal to b here and get the correct answer, right?
Yes, sir.
Hmm. So then it will be correct.
Okay, sir.
But this is a more generic example. So if only was not there, then this would have been true. So this option is false. So my correct answer here will be both A and B are wrong.
Sir,
Yeah.
one more doubt, sir, regarding
Yes.
RTT.
Yes.
Um, in the assignment, there was like similar problem
Hmm.
regarding the where we can apply RTT. In there, it was mentioned that it can be used both in solids and fluid.
Yes.
Is it correct, sir?
Yes, definitely. It can. It is not limited to my fluids. It can be used in any control volume situations. So when we are like understanding or like writing down the RTT equation, we have not never mentioned or like taken the assumption of the material being a fluid. So only thing that we have done is taken a control volume and said that like some property, it's a B. How is it comes up? So one thing that can happen is B value can rise. The B value can rise or fall within the system. So that's why this uh, ddt of this B inside my volume is coming into the picture. Plus what can happen? Flux inside and outside. So flux for flux, what I need to do? I need to do this, right?
But for solid, will there be flux, sir?
Uh, so let's say when we are talking about solid, let's have a moving control volume. The solid is stationary, let the control volume. Then definitely there will be some flux in or flux out. And like this is not a very practical example because where will you use such an example? But let's say the solid is deformed. Solids can also deform, right? Under stresses, solid undergo deformation.
Yes.
But their deformation is different from fluid deformation. Why? It does not flow. So their deformation is linked with. So there the deformation is linked with my displacement. So S variable is generally used. So displacement is used for deformation. Like for example, you are doing universal testing. So a rod is there, you are applying a force. So this is deformed, right? So if your control volume did not include my deformation element, what is happening? This solid is moving out of the control volume, so there is a flux, right?
Okay, sir. Yes,
Hmm.
sir.
So this is Reynolds transport theorem is generic for any material. It has, in fact, it is also since this is an integral form of equation, we don't also need to really bother about whether my material is in continuum regime or not. Even if it is not in continuum regime, then also this will be still valid because it's taken in an integral sense. When we are arriving at the continuum our equations, our fluid equations, what we are doing, we are shrinking the control volume. If continuum was not valid, then we would not have been able to shrink this control volume. That's the only difference. Otherwise, general Reynolds transport theorem in its integral form is valid for all materials, for solids, fluids, and also for materials where we cannot uh, apply our continuum hypothesis. Okay.
Yes, sir. Thank you, sir.
Okay. Yeah. So here the explanation is given for this uh, the question that we have got. You can go through this. Alright. Uh, let's uh, let's see our second problem. So here is a numerical problem. It's given 4 feet high and 3 feet diameter cylindrical water tank is there, and it's open to atmosphere. So you can draw this. So a water tank is there, and its height is 4 feet and diameter is 3 feet. And a discharge plug near the bottom is pulled out, and the water jet diameter zero point 0.5 inch. Okay, so this is inch. Uh, yeah. So this is inch. Streams out. An average velocity of the jet is approximated as this, and where h is the height of this. Also, you can derive also this is taken from your Bernoulli's here, right? You can apply your Bernoulli's, you will get the same answer. And where h is the height, and all the values are given. So what I have to find? Determine how long it takes for the water level to drop to 2 feet from the bottom. So it was initially the water level is initially 4 feet, and it will drop to 2 feet. So half of this will get empty through this plug. Okay. We are also told to assume two things. Let's discuss this assumption. So the distance between in the bottom of the tank and the center of the hole is negligible. So basically, 2 feet means 2 feet from the bottom, and when we are calculating this h, this velocity h, this also we will take as this height from the bottom. So the whole diameter is negligible compared to my height of the water level at any point. So 2 feet is the minimum. So 2 feet and zero point 0.5 inches, there is a lot of difference. So we can simply assume that to be negligible. Okay. What's my second assumption? Second assumption is okay. So the first assumption was water is incompressible. That's fine. Third assumption is the gravitational acceleration. So that's good. Okay. So tell me how to approach this problem. So here my uh, uh, velocity of the jet that will vary, right? Because h is decreasing, and that's my main challenge for solving this problem. So this velocity will vary. So how to find out this velocity? Like establish a relationship between this and the height. Hmm. So the way we can do this is using my continuity equation or conservation of mass equation. So let's say at any moment of time, let me add a blank. Yeah. So draw this side. So let's say at any point this height is h, and the velocity outlet here is v. So v is the velocity from here. So if I take this as my control volume, if I take this as my control volume, then what is my mass outflow? Mass outflow here is integration v dA into rho. Yeah, rho will be there. Density will be definitely there. So rho v dA. So this is my outflow through this. So this outflow, this will be equal to the water level declining, right? So the declining water level, what does this indicate? What does this indicate? This indicates um the decrease of mass inside the control volume. So for the decrease of mass inside the control volume, we will have this both will be in the same cell. So we are applying my Reynolds transport theorem, the Reynolds transport theorem. So, so this, so for the decrease in this, so ddt dv plus dv. So I'm not writing n cap dot because this is exiting normally here. This is equal to 0. So so rho is constant. So integration dv is like the volume of this, the water is decreasing. Right. So volume of the water is decreasing. So for that, I will have this area of the tank, let's say AP and into DHT. Let me take this side. So this will be the area of the jet. AJ. So this is my like equation. So I can substitute here my V as the minus sign is there, my root over 2G. So you can calculate, rows will cancel and you just need to integrate this. You will need to integrate this. So root h. So what is the question? Question is determine how long it takes. So time is being asked. If time is being asked, let's take time on one side and the rest of the terms on the other side. So if dt is this side, uh, then minus at by aj dh by root over 2. You have to integrate this 0 to t. So this t is what we need, and this will go from h is equal to 4 feet to h is equal to 2 feet. So can you like calculate and tell me? So for AT is 5 d of 10 by 4, the square. And this tank diameter is given as 3 feet. And similarly, the jet diameter is given as 0.5 inches. So 0.5 inches means 0.5 by 12. And G is 32. You can take G as 32 feet per second.
Sir, is it 750 seconds?
750 seconds. Can you tell me like the result of this integration? So dt square is there, dt square by dj square. This is there. So the minus sign will go away. So root over 2g minus sign will go away because this is minus half. So uh, to accommodate for that, there will be another minus sign, right? And this will be root over h. So let's say this is like h1 minus root over h2. And another 2 will be there, right? 2 will be there. Is this correct? If there is any mistake, please let me know.
I got the term as 1292, sir, that diameter when simplifying.
This diameter as, sorry,
That
could you repeat?
the outside term I got as 1292.
Okay, okay. You had put the values in.
Yes, sir.
Okay. So what's the answer? 750.
Yes, sir.
Okay. So you are getting around 750 seconds. Okay. Is it one of the options? Yeah, it is one of the options, right? Option B. So let's check. Yeah. That is the correct answer. So we can like check how they have done, like what's the given in the solution. So same continuity equations we have to use. There is no mass inlet here. So mass inside the control volume is decreasing due to the dropping water level, and that is we have to equate it with the negative of the mass output. Yeah. So same thing was there. Yes. So basically the same expression we had got. Just if you put the values in, you will get the correct answer. Is there any question regarding this problem? Let's move to the next one. So an incompressible flow through the device. So the device figure was not there. Drawn this. So the velocity may be considered uniform over the inlet and outlet sections and following are given. So there are three sections. So two inlets are there, one outlet is there. So the third section is the outlet, and two inlets are there. So what will be the equation? No, we don't need to always like write the elaborate Reynolds transport theorem. This is pretty straightforward, right? So the if mm, it is an incompressible flow, my densities are constant. So uh, rho I can cancel, right? It will be rho v1a1. This is the mass inlet through my first inlet plus rho v2a2. This is my mass inlet through uh, mass flow rate through my second inlet. This will be equal to the outlet, right? So rho v2 a3. So rows will cancel, and so v3 this is equal to v1a1 plus v2a2 divided by a3. Can you tell me which option, like which it matches with?
So, A.
It's matching with A, right? So, like the functions won't change. The functions will definitely remain the same. With this time functions. So, uh, with this, we can identify whether they are talking about the first inlet or the second inlet. So, for this exponential function, uh, we have 10 into zero point 0.1, which is 1, divided by 0.15. Yeah, so this is 6.66. And this, for the second term, this is 2 into zero point 0.2, which is zero point 0.4 divided by, so it's around 2.5. Yeah. So first option is correct. This is pretty straightforward. So here in question number 4, we have this inclined plane. So oil is flowing in a thin layer down an inclined plane. The velocity profile is already given. The coordinates are marked. So what we need to find is basically the mass flow. Uh, so can you tell me which this symbol is there? What does this symbol signifies?
Free surface.
Yeah, this is the free surface. That means the pressure here is atmospheric, right?
Yes, sir.
Yeah, atmospheric, provided basically the curvature is uh, there is no curvature, so the pressure here is exactly as atmospheric. Why did I mention curvature? What would happen if there was a curvature on the surface?
So then we have to take the pressure at horizontal and vertical surface.
Then you will have a pressure jump. If there is at equilibrium, if there is a like curvature, if there is a curvature, then basically you need to take a Laplace pressure jump due to the surface tension. Otherwise, you will have smooth surface. Okay. So mass flow rate. If, do you have any doubt regarding that? Just what we have discussed. Okay. So mass flow rate, how we can calculate? We just have to integrate along this. So this will be rho density, u is the velocity, and this we will integrate over a cross-sectional area d. Now, since it is given per unit width, so if it is given per unit width, what we have here is basically rho u dy, because the width is unity, it's one, and it's not varying across that direction. It's a two-dimensional flow. So why we have to integrate from 0 to h. U's expression is given, so we can simply put that expression. I will carry forward it here. So I'm taking everything out which is not a function of y. So in u also there is a rho, rho square j. So this is y dy. So y dy is y square by 2. So y
Option
square,
C, sir.
yeah, tell me.
Option C.
So this is half minus 1 by 6, right? So this is 1 by 3. So option C is correct. 1 by 3. Sin theta is this cos theta and tan theta, these are technically wrong. Uh, Theta will not be inside this interval. So why is this velocity profile like this? There are a few things that is going on here in this velocity profile. So one thing that we can be very sure of is no slip condition has been applied at the particular wall, and highest velocity is definitely along the surface, which will be highest velocity is at h, and at h also you would have your del y as 0. Because it's a free surface, no stresses are transmitted across it. Right?
Yes, sir.
Yeah, you can check that if you want. So if you take del y, then del y at del u del y basically at h is 0 for any shear stresses. Where is I cannot find my thing. Yeah, I can find it. So yeah, that's one thing. And rho g is there. Rho g sin theta is there. This term is here because this particular fluid is moving due to its own gravitational weight. Hmm. So its own gravity is driving it downwards, and mu is there. That signifies its viscosity is limiting its flow, right? And since it is not varying across x, we can safely assume it's not varying with x, right? So this is not changing with x. So it has assumed a same velocity throughout its inclination. That means there already a balance between my viscous term and the gravitational term which is driving it downwards. This balance has been achieved. So if you solve such type of flow, you will get this kind of a velocity profile for thin film surface. So you can like the exercise like the discussion that I did. You can do that. You already know your like Navier-Stokes equations, some forms of it. You know, you can put this term hmm, using your viscosity, and you will have a rho g. Hmm. So in this case, you will have rho g sin theta, right, which is acting along the slope. Uh, you don't have a pressure gradient, so this term will go away. This term will go away. So you can basically this the reason this term goes away is little bit non-trivial. So what you have to do is basically do a scaling analysis, and if it is a very thin film, if it is a very thin film, then you will see that uh, uh, the inertial effects are very negligible when compared to your gravitational and viscosity. So if you just balance these two, you will get this kind of an equation. So you will have something like this. You may find Professor Chakraborty's lectures on such kind of flow itself in YouTube, where he discusses about this flow. So this actually would be minus because it's driving here to the. So if you solve this, you will get this kind of an solution using appropriate boundary conditions. Let's go to the next question. So in this question, we have a spherical tank. The volume of the tank is given, and there is a valve which is containing this air inside this tank. The valve is opened, and the velocity through which the air escapes initially is given, and air temperature and pressure is given. So we have to find is rate of change of density uh, of the air in the tank at this moment. Do you understand what this question is asking?
d rho by dt.
Hmm. This question is definitely asking d rho by dt, right? Changing rate of change in density. So how will we achieve like uh, try to find that using our conservation of mass, right?
Yes,
So
sir.
yes, why is this given? The temperature and pressure. Why is that given?
Because compressed air is used, density will be varying.
Hmm. Density will be varying. That we have to find out rate of change of density. So do we need this temperature and pressure? We will need it for the initial gas that escapes. So the equation that we will have is changing mass inside this uh, balloon, right? It's not a balloon; it's tank, so its volume is not shrinking. So its pressure is shrinking. So we will have this changing mass inside this inside the chamber. So the mass will be decreasing, and there will be mass which will be going outside. Right, mass inlet is not there. Correct. So this is rho into volume of the tank. Whereas this is rho, but this rho is not like we can since it is asked to find out the change in air density at this particular moment, so we can assume it to be this uh, the initial density. We will assume it to be the initial density. Otherwise, what we have to do is basically take this as my variable, solve this differential equation. We will get a density variation with my with time, and then solve the equation separate like that. Hmm. But the a problem will be there because my velocity will also vary with time, and I don't have that relationship. So what I will assume for simplicity, I will assume this density as my initial density. So this is my initial density. I will have the initial velocity which is given. So uh, let me put this here. So this is used to differentiate it from my velocity. Velocity also I am using v. So volume I will use this a cut sign here to distinguish it from my velocity. And the area will be there. Area is given. So volume is constant. So d rho dt, and this is equal to uh, minus y volume. So to find out this rho initial, we need to use my temperature and pressure from my ideal gas equation. That's why this ideal gas equation is given. So what's my ideal gas equation? My ideal gas equation is pressure to R rho T, right?
Yes, sir.
So R you can take as 8.3 is a unit. We can calculate this. This is
Sir, option B.
Option B. Okay.
Second option. Yes.
Yeah. So, so let's check the order of magnitude of this. So 3 into 10 to the power 3, there is 10 to the power minus 4 here. So 250 and 253 are almost same. Uh, so, so this is coming approximately as uh,
Sir,
mhm. Yeah. Tell me.
R we should take as 8.3 or 0.287.
R how much should we take?
8.3 or 0.287.
Uh, 0.285.
For air, we take R as 0.287.
Oh yes, we are not taking using molarity, right? Okay, I'm sorry. Yeah. Yes. Uh, this is wrong. This we will take when we are discussing in terms of like molarity, but we are not doing that. So definitely, since it's in terms of mass, we will take my gas constant for air specifically. So that is point 2, right? 28. How much is that?
287, sir.
Yeah, correct. Thanks for pointing. Okay, you are getting option B.
Yes, sir.
Okay, yeah, that is 0.287. Let's move to the next question. Okay, so this is also a conservation of mass problem. So we have a flow faster porous flat plate, and at the bottom of this plate, water is leaking out with a velocity which is mentioned. Mm, we have an inlet velocity, and since the plate is there, a boundary layer develops, and we have the mm, velocity profile at the outlet section given. So what we are asked to do is evaluate mass flow rate across section BC. So section BC is this BC. So this section is my section BC. Yeah. So let's calculate that. So this is given as 0.5 mm, and this is 3. So these are constant velocity. So in the porous plate and the inlet, these are constant velocity. What we need to do is basically multiply the velocity with the length. We are multiplying with the length because it is like given as two-dimensional flow. Hmm. There is no variation along the z direction, so we will just take unit width and solve. So only thing that we need to take is the length, and we will assume it to be incompressible, so there is no change in my density. So only thing that is to be calculated is flow through the outlet, so that will be integral, an integral. So this will be integral u dy from 0 to delta. Delta is there. So u is mentioned here. So u infinity I can take out. This is 0 to delta 3y by delta minus delta to the power 3 by 2. So this is integration with respect to dy. So u infinity delta will be there, and there will be some coefficient. So the coefficient will be here in the first term it will be y square by 2, so 3 by 2, and here this is to the power 3 by 2, so 2 by 5 will be multiplied, right? So how much is this? This is 0.7. This is 0.7 into delta. We have u infinity delta from this side, exiting 0.7 u infinity delta from this side. So from this inlet and outlet, we have 0.3 u infinity delta getting in, minus this is getting outside. So this is uh, 0.2 millimeter per second into 2. Let me keep it as v here. This is going outside. Uh, so this will be equal to the amount that is going outside, right? The mass flow rate which is going out. Correct. Divided by my density, because density I have not taken anywhere. So density will definitely be. And
Sir,
tell me,
option B.
yeah, option B,
B.
1.42.
Yes, sir.
So this is 1.35 minus zero point 0.4. Like in this calculation, is there any mistake? Can you, or like have you done this calculation this way or like any other different way?
Sir, VL, it should be positive, no, sir?
Mm, VL is going
Ah, no, sir.
outside.
Yes, sir. Right, sir.
Yeah,
Right.
it is negative.
Right, sir. Same, sir, equation.
Okay. So if you put the values, then this is coming out to be 1.42 into 10 to the power 3, and then rho you are multiplying 10 to the power minus 3, and rho you are multiplying as 10 to the power 3. Is that correct?
So you missed the width term, sir, W.
Is W given?
Yes, sir. In the picture, in the side.
Oh, okay. Width is given. Okay, all right. Yeah, I assumed unit width. Okay, so W will definitely will be there in all this terms. W will be there. W is there. So okay. So this is 1.42. Yeah, then it is checking out. So this is 1.35 minus this is about zero point 0.4. So 0.95 divided into 1.5, right?
Yes, sir.
0.95 into 1.5. Okay, it's checking out. So it's 1.44 kg per second. All right. So let's move to the next question. So an incompressible inviscid flow flows into a horizontal round tube through its porous wall. So let's keep on drawing as we read the question. So the tube is closed at the left end. So left end is closed, and the flow discharges from the tube to the atmosphere from the right. So at the right, the pressure is P atmosphere. The P atmosphere pressure is there, and the flow is taking place through this porous walls, right? Flow is entering through the wall. Positive x-axis is measured from the left end, and from this end, positive x-axis is measured. Uh, the density of the fluid is given, the diameter and length are given. Uniform inlet velocity, so this inlet velocity is given as v0. The flow is steady. So the x component of acceleration of a fluid particle is asked. So what are we supposed to find? We are supposed to find the acceleration. So acceleration of a fluid particle we have already discussed. So x component ax. So this will be du dt, right? Where d is capital. So this is the material derivative. So here we have del u del t, this term, plus u del u del x plus uh, the other term. So let's like here radial cylindrical coordinate would be preferable, but like let's go ahead with this itself. Del u del y w w. So if it is steady from symmetrical arguments, actually we can uh, 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 like argue that these variations along uh, why the fluid velocities that we have considered here. So these can be neglected. So first of all, steady state is there. So this is zero, and uh, del u del x is definitely there. There will be a variation of the x component velocity along my x direction due to the inlet of inlet of the water from the sides. And what we can assume for simplicity is that these components, this y acceleration and so these components, this v del del y and w del del z components, to be negligible compared to my x directional velocity component. So if we neglect this, then what we have to find here is simply u del u del x. So to find this, first we need to find what is u. And this u will be a function of x. So how to do it? So let's take an arbitrary cross section, arbitrary control volume uh, at length x. So its left wall is closed. So we will take the left edge of this control volume right along the left wall, and we will take its right edge at a some distance x. So this x, if we vary, we will get my velocity as function of x. That's why I have taken it an arbitrary x. So if we calculate the flux from there, we will have to use the velocity at this x, and from that velocity of this x, if we isolate that, we will get its expression, and that is what is required. So what will be the flux going out? It will be rho u, which is a function of x, and the area along this. So what I am doing is I am using this assumption that they have already said. For simplicity, consider the x component of velocity in the tube uniform across any cross section. Otherwise, I would have to integrate this along my area, and that would complicate things. So what they have asked is to basically keep this u uh, as constant along the cross section. So it's like taking an average velocity. So, what we have is basically rho u into area. So area is given, the diameter is given d. So this is 5 d square by 4. This is the mass flux going out. What's the mass flux coming in through the walls? So mass flux coming in through the walls, this will be equal to that mass flux coming in through the walls. So density will definitely be there. The velocity will be there, v0, and the area will be there. Area here is also like constant. It's a function of x, but x is constant when our control volume is fixed. So if the control volume is not changing because we have taken control volume length as x, so if the control volume is fixed, that x is fixed. So we can also like take the v out and do this integration. So here we are only in the Reynolds transport theorem. We are only using the flux term. So the mass variation inside the control volume is not happening here. Here only there is a mass inlet and there is a mass outlet. So 0 and uh, this area will be length, which is x, into the circumference. So circumference will be 5 into d. So x is there. So if I just separate out u, so this u will become 4 v0, 4 v0 by d. Any other term is there? Rho is cancelled. Pi is
X,
cancelled. X is there. Definitely x is there. It's a function of x. So it's a linear function of x, and that is expected. If I uh, like supply uniform amount of mass, uniform velocity is there along my x direction, so my velocity will keep on growing linearly as I am moving along the x direction. So can you tell me how much will be then del u del x? U del u del x.
sir, option A.
Option A. So del x when we do it is simply 4v0 by d. So this will be 16 v0 square by d square x. So this is option A. Yeah. So they have done it this same way. Yeah. So they have neglected this the velocities here. The x and y component velocities are neglected. So this is an assumption here. So there might be some amount of x and y velocity, but since we are already considering that in the x component velocity is uniform across the cross section, we can like safely assume that any water inlet that is the water inlet that might be causing any uh, velocities in the other directions. So those can be neglected, and x component velocity will be much larger than any such other components. Okay, yeah. So uh, another question is there. So in the previous problem, so it's referring to this previous problem, the expression for the gauge pressure at x is equal to 0. So we had this. So outlet, so L was the length, right? L was the length that was given. So at the end of this tube, the pressure was P atmosphere. And this is x is equal to 0 at the left edge. This is x is equal to 0. So what we are asked here is expression for the gauge pressure. So if pressure is asked here, what we have to use? We have to use the
Euler's
Euler
equation.
equation. Yeah, the Euler's equation we have to use. So Euler's equation. Why Euler's equation? Not the generic Navier-Stokes. What we are assuming here, we are assuming that the flow is in invisible. So viscous effects are not there. So del u del du dt. So I am writing only the x component of the Euler's equation here. So because that is only required. We are neglecting the other component. dp. It's since it is steady and I am neglecting other components, I am writing the partial derivative as my full derivative. So it is generally this, right? Del Lx of p. But what is p as a function of? P is a function of x, y, z, and time. These are the variables the pressure can be a function of. But here we are assuming the pressure is not a function of y, it's not a function of z, and it is already given that it is steady, so it's not a function of t. So since it is a function of only one variable, we can safely write this as dp. Okay, plus any body force term. So here, is there any body force term? There is no body force term as such. The flow, what is driving the flow? Flow is just driven by the inlet velocities, and that inlet velocities we have already taken care of when we had solved the continuity. We have solved for conservation of mass. So here it is not required separately. Okay. So we have already seen what the left hand side of this of the equation is, right?
Yes, sir.
So this is simply rho del u. Uh, this this is equal to minus dp dx. So can you 16 rho v0 square by d square, right? Into x.
Into x.
This is equal to minus dp dx. So dx will go this side and we will integrate. So x dx integration. Uh, so if we are integrating from, let's say, 0 to L. So if we are integrating from 0 to L, this will be L square by 2. Right? And what will happen here? If we are integrating from 0 to L, then this is the pressure required minus P atmosphere. Pressure this minus P atmosphere. So this is the pressure gauge. Right? Oh, 0 to L. At L, the pressure is atmosphere. So this is minus of pressure. This minus of gauge pressure. So pressure at L, which is P atmosphere, minus pressure at x is equal to 0, which is the pressure required. So this would be minus of gauge pressure. So which option is correct? Option
Last option.
D is correct. Yes. It's the same concept. Is okay. So this was the last question for this session. Uh, Let me know if there is any questions that you want to ask.
Sir,
Yes.
sir, in question 4, you said that for a curvature, the pressure will not be constant. Can you please repeat it, sir, what you
Yes,
said?
definitely, definitely. So here, what I was basically referring to is the free surface, right? We were talking about the free surface.
Yes, sir. Then you said about curvature, sir. That part.
Yeah, here are a lot of spaces there. So when there is free surface, we denote it like this. Then there is no stresses that are exchanged between these two surfaces. So shear stresses are zero. So any the velocity profiles, whatever velocity profiles we will have, if this direction is y, so all this del u del y, this will be zero. So that will be there, and what else will be there? The pressure here and pressure here will be same, constant ones. The pressure outside the interface is equal to pressure inside the interface. If it were curved, that would not have been the case. If it was a curved surface, then pressure here and pressure here would not have been the same. Why? Because we know that if this is the case, then there is a pressure jump. So if it is point 0.2 and point 0.1, then there is P2 minus P1. This is equal to my surface tension gamma into my curvature, some kappa. But this is the curvature. And if I can like find the radius of curvature along any two orthogonal directions, then I can also write it as this, which might be a little bit more familiar to you. Right.
Yes, sir.
Hmm. So if there is a curved surface, then the pressure at outside the curved surface and like inside the curved surfaces are different, and that's why the surface is curved. Basically, one side there is some excess pressure which is pushing the surface from its like plane nature. So it is pushing the surface to make it curve. The pressure is kind of pushing the surface, and at some point of the curvature, it is attaining equilibrium. So the equilibrium is attained between the surface tension forces and my pressure difference. Hmm. When there is a plain free surface, there is no pressure difference. Okay.
Okay, sir.
Hmm.
Thank you, sir.
Okay. Is there any other question?
No, sir.
Okay. If there are no other questions, then I will close this session. Okay. Thank you. We'll meet again in the next one.
Thank you, sir.